This is the p-series test, and a p-series is a series that looks like this summation of 1 over n to the p, where p is a positive constant. So we're looking for some positive whole number as an exponent in the denominator. And the p-series test says that if that positive constant, I said positive whole number, not positive whole number, just positive constant number. If that positive constant exponent in the denominator is greater than 1, then we get convergence. So like 1 over n squared. In that case, the p-value is 2, which is greater than 1, therefore convergence for that series. Like 1 over n to the 3 halves. In that case, the p is 3 halves, which is greater than 1, therefore convergence. If the p-value is less than or equal to 1, then we get divergence. So if we have 1 over n, in that case the p-value is 1, divergence. If I have 1 over n to the 1/2, in that case the p-value is a half. Again, we get divergence. The idea here is how fast the denominator is getting large for these series determines whether we get convergence or not. So in the case of 1 over n squared, if we plug in a few values, plugging in 1 gives us 1, plugging in 2 gives us a fourth, plugging in 3 gives us a ninth. And for 1 over n, which is also called the harmonic series, plugging in a few values gives us this series. And the top series converges, whereas the bottom series diverges. And the difference between the two is in the top series, the 1 over n squared series, the denominators are getting larger faster. And if the denominators are getting larger faster, the fractions are getting smaller faster, fast enough for convergence. And in the bottom series, the denominator is not getting large fast enough for the terms to get small fast enough to get convergence. So in that case, we're getting divergence. Small and fast and large are all relative terms. The proof for this really then would come from the integral test. And if we integrated 1 over x dx, we would have natural log of the absolute value of x from 1 to infinity, which is going to end up being infinity. So then we have divergence for that series, that's 1 over n. Whereas if we integrated 1 to infinity for 1 over x squared dx, we would end up with negative x to the negative first, evaluated from 1 to infinity, which is negative 1 over x, evaluated from 1 to infinity. And then as I plug in infinity for x, this term is going to 0, and we end up with a positive 1. So then we end up with convergence for that second improper integral, which then means convergence for the series 1 over n squared. So then looking at this series, listing out a few terms, the first term is 1. The next term is 1 over 2 square roots of 2. The next term is 1 over 3 square roots of 3. We don't have a constant ratio, so they're not geometric. If we did the nth term test, the bottom grows to infinity and the top's a constant 1, so we get 0, which means inconclusive for the nth term test. We could integrate this from 1 to infinity. But that's going to be more work than we need to do. And when we learn more tests, integral test really is going to be the last test that we want to try. If all else fails, then we'll do the integral test. But if we can avoid doing it, then we should avoid doing it. So the test that we're going to use here is p-series. Maybe this doesn't look like a p-series, but then we want to answer the question, can I rewrite this 1 over n square root of n as 1 over n to some exponent? And n is n to the first, square root of n is n to the 1/2. So then n to the first times n to the 1/2 is the same thing as n to the 3/2. So then that exponent we could write as a 3/2 power. So we could write this series as 1 over n to the 3/2. And then we see that this is a p-series. P equal to 3/2, which is greater than 1. Therefore, this series converges by the p-series test. That is p-series.